Discuss the chemical structure of xanthan gum and various groups which are present in the chemical structure of xanthan gum. What is the relation of these groups to its suspending effect, emulsifying effect, stabilizing effect, and thickening effect, and why suspension of xanthan gum is more clear than the suspension of guar gum. We will also discuss two important mechanisms of actions of xanthan gum, how xanthan gum perform its stabilization mechanism for syrup and semisolid dosage form, and which other type of excipients are also helps xanthan gum to perform its better stabilization mechanism. We will also discuss some important incompatibilities of xanthan gum which may be ignored by healthcare professionals but they cause major problems in the product. Hello viewers, welcome to my channel. I am Mudassir Abbas with another topic related to suspending agent. Today we will discuss some important groups present in the chemical structure of xanthan gum and their relation to its properties and mechanism. Xanthan gum contain many important groups. It contains hydrophilic groups, it contains cationic groups, it contains acetate group, carboxylate group, and pyruvate groups. These groups are important groups present in the structure of xanthan gum. First of all, thickening effect of xanthan gum is related to these hydrophilic groups, that are hydroxyl groups and CH2OH groups. When these groups captures water, they hydrogen bond with water, then they make a big large molecule of xanthan gum, due to which xanthan gum is thickened. Second important group of xanthan gum are these cations. These cations are in fact the part of this carboxylic group and this uh, pyruvate group. These cations have property to make pi-cation interaction. Pi-cation interaction is formed between cation and pi bond. Pi bond is in fact one of the bond in double bond, and there are most of the lipophilic substances that contains double bond, due to which xanthan gum makes interaction with the double bond through its cation, and pi-cation interaction is very strong interaction. It is 4 to 10 times stronger than the hydrogen bonding, due to which when pi-cation interaction is formed, then it captures the system very strongly and entire system is stabilized. Lipophilic and hydrophilic substances present in the groups are evenly distributed and mixed and stabilized. Pi-cation interaction is formed in fact due to the attraction of cations toward the pi bond, because pi bond is abundant with electrons, because it falls in p orbital and p orbital contains abundant electrons and electrons have negative charge, due to which pi cation interaction is formed between these two groups. This interaction results in emulsifying effect and stabilizing effect given by xanthan gum. Xanthan gum also contains some important functional groups. It is the carboxylate group of xanthan gum. This carboxylate group is involved in adhesion of xanthan gum. This carboxylate group is also involved in electrostatic stabilization mechanism of xanthan gum that we will discuss onward. This acetate group of xanthan gum is unstable with phenols. There are some active ingredients and excipients that exist as phenols. This pyruvate group also has negative charge. It is anionic in nature. So, these two groups that are anionic in nature are also unstable with certain cationic polymers. However, these two sites are useful in electrostatic stabilization mechanism of xanthan gum. Guar gum contains no carboxylic group. It is not anionic in nature. Here we will discuss the mechanism of action of xanthan gum, mechanism of stabilization and suspending action of xanthan gum. Xanthan gum stabilizes the system through two mechanisms. One of it is steric stabilization and other is electrostatic stabilization. Steric stabilization is related to repulsion of xanthan gum molecule through osmotic pressure, while electrostatic stabilization of xanthan gum is related to formation of positive and negatively charged active ingredient and excipients around the carboxylate group, around the negatively charged group of xanthan gum. Steric stabilization occurs in such a way that water molecules form hydrogen bond with abundant hydroxyl and CH2OH groups present in xanthan gum, due to which quantity of water becomes high within the molecules of xanthan gum, because xanthan gum molecules are also highly entangled with each other, due to which they capture large quantity of water, as a result of which large quantity of osmotic pressure is developed within the molecules of xanthan gum, while osmotic pressure outside the xanthan gum molecules is less, due to which osmotic pressure within the molecules of xanthan gum repel the water, because water moves from its higher concentration to the lower concentration, as a result of which repulsion occurs between the molecules of xanthan gum and between the water and xanthan gum molecule. On other hand, xanthan gum molecules are absorbed on various species which can react with each other. In this way, xanthan gum stabilizes reacting species because it, through its long chain molecules and abundant captured water molecules, repel other xanthan gum molecules and reacting species remains away from each other. Another stabilization mechanism of xanthan gum is electrostatic stabilization mechanism. Electrostatic stabilization mechanism of xanthan gum in fact starts from carboxylate group, because carboxylate group contains negative charge and various positively charged molecules present within the system reside and are attracted toward the negatively charged molecules. Just like if it contains certain weak acid, and if this weak acid is ionized, then these ionized components contain both positive and negative charges, and these positive charges of these weak acids and weak bases are attracted toward the negative charges of xanthan gum and they form the layer. Similarly, negatively charged component of weak acids and weak bases are attracted toward positive charges and they form another layer. And the same way this process is continued, and at last there is a great distance between the reacting species on which xanthan gum was absorbed, and hence the system is stabilized and the reacting species are much away from each other and they are secured and covered with the positive and negative charge layers, due to which system is stabilized by xanthan gum. Guar gum contains no carboxylate group, due to which this stabilization mechanism of electrostatic stabilization does not exist in guar gum. Guar gum contains only steric stabilization mechanism, and hence due to electrostatic stabilization mechanism, xanthan gum makes an organized system because it takes its complete family of excipients along with it in an organized way, and hence the syrup formed by xanthan gum is more clear and shiny. But in case of guar gum, there is no organized system and it is a scattered system because it contains only steric stabilization mechanism. This system is relatively less clear and more turbid. Xanthan gum is commonly regarded as stable excipient, but xanthan gum has some important incompatibilities that may be ignored by healthcare professionals, which may cause problem in its product and hence market complaints. One of important incompatibility present in xanthan gum is reaction of acetate part of xanthan gum with phenols, like paracetamol is a phenol. Similarly, parabens like methyl paraben and propyl parabens are also phenols. And there is a reaction between uh, acetate and phenol, and this reaction is known as phenol acetylation. When these two molecules react with each other, then they form a new molecule, and this new molecule has different chemical nature. It is not the active ingredient which was added into the product. Hence, if paracetamol is added, it reacts with xanthan gum through its acetate component, and hence a new product is formed that is in fact not a paracetamol, and this product recrystallizes and settles down. This incompatibility exists between xanthan gum and all phenols. When paracetamol suspension is manufactured with xanthan gum, then paracetamol suspension settles down due to reaction with acetate groups. So in such case, certain other stabilizing agents like acrypol and gum tragacanth may be used to stabilize the paracetamol suspension. Xanthan gum is also unstable with parabens like methyl paraben and propyl paraben, and many pharmacists may add parabens in suspension that contains xanthan gum as suspending agent. So reaction will occur between parabens and acetate part of xanthan gum will result in inactivation of parabens, and new compound will be formed that will not be a preservative. Hence, your syrup will lack the preservative and microbial spoilage of the syrup will occur and market complaint may be received in such case. Another important incompatibility that may be ignored by healthcare professional is incompatibility of xanthan gum with cationic polymers. Cationic polymers may be CMC sodium, it may be sodium alginate or any other polymer that is cationic in nature. So xanthan gum contains carboxylate group that is anionic in nature, but cationic polymer when is attracted toward carboxylate group, then due to having large bulk of these two polymers after making bulk together settles down. Hence these are incompatible with each other. In fact, this carboxylate group attracts positively charged groups if these groups are small, like ionized weak acids. If these groups are small, then there is no problem and these groups will help in stabilization of xanthan gum. But if these groups are large, like polymers, then in that case they will make together a large bulk and will settle down and will destabilize the system. Similarly, xanthan gum also has property to react with alcohols, like carboxylic group of xanthan gum when react with alcohol. This reaction is known as Fischer esterification. Let's suppose if you are using any alcohol in your semi-solid dosage form or in syrup. So in that case, these alcohols will react with xanthan gum through its carboxylate group, and they will result in formation of new compound, and your alcoholic constituent will lose its efficacy.